One, because I broke things really bad yesterday, is part one. And part two is this will be a fun experience. And all the answers are actually not far away, hopefully. So this will look a little bit more like a traditional lab from the Chip Whisperer group, because it's one of their labs. So let me also share my screen here. Lab courses open for you. So I don't anticipate this lab taking everyone very long. So I'm dealing with the fact that Zoom wants to share all my browser windows again. So, let me know what you see. Do you see all my windows? Or do you just see one, hopefully? This says recent announcements. Okay. Whatever UI enhancement they've made is honestly beautiful. Okay. So you can find this under modules or under assignments, as always. What you'll notice, first of all, I did go ahead and add into Lab 5 video recording. Obviously, I posted that a couple days ago on other spaces, but I've also added in the code key for the lab. So you can actually look at all the code that I generated last time. So you can double check it if you want to. Now, it doesn't help you with any of the text portions or any of the questions that I asked throughout, but at least the code, you can double check what you've got. But there is a new module called glitching. And this lab is pretty straightforward. So original lab is going to be on masking based off of the state that I put my Chip Whisperer in yesterday, how long it took me to recover. Decided that was not a good idea for now. I'm going to try to develop something that's a little bit cleaner and something that you can actually use without fear of actually breaking your device or spending hours trying to recover it. So with that said, we are going to swap basically what we're going to do with starting to talk about glitching, which is kind of fun. So the way you're going to do this is you're going to start up your Chip Whisperer environment just like you would normally. So the only difference from what we normally would do is you're not downloading anything from me at this point. You're going to start up your Chip Whisperer environment. And that basically includes your notebook and hopefully your trusty Chip Whisperer Nano. Hopefully you still have that somewhere nearby. And you're going to navigate to Notebooks, Jupyter, Courses, Fault 101. So there's a fault directory hopefully in there. So let me make sure to do that. And we're going to be doing 2 notebooks. All right. We're going to be looking at fault 1_1, so the first notebook in the series. And everyone should work through section 1.4. It's actually mostly reading to understand what a glitch is. All right, so great pictures and things like that. Now, part 1B is optional for all the undergraduate students in 4010. Optional, okay? Required for all the 5010 graduate students. And while I can't require it, don't want to require it, highly suggested for future graduate students, really anybody who thinks they're ever going to do experimental work of any kind. So part 1 is literally just reading through to understand what glitches are. Part 2, continue running past section 1.4 in the notebook, and what you'll notice is that a lot of the cells will work, they will execute, no problem, but at some point in the lab, it will break. And it will break hard. And I'll leave it up to you what you do with that. You can either spend some time trying to fix it, go through the process, go through your own internal process to see how you handle this situation, right? Imagine that you've been placed in a new research lab or you're a new graduate student and an advisor or somebody, I mean, this could even be in a research lab outside of the university setting. Somebody tells you, okay, hey, we've got this experiment, go run it. You run it and you run into this problem. What are you going to do? And to give you a hint, but what I want you to do in the last notebook at the cell for that one is detail what you think is happening, and then find a reference somewhere that proves to your advisor, lab director, boss, whatever, that you need different equipment. And if you are a grad student and you see this, or if you've had experiences in the past, you'll understand why this is really important. All right. It's not always your fault, but if it's not your fault, you've got to prove it. All right. So again, part B is optional, but you know, I highly encourage you to take a look and see what you can find out. All right. So honestly, this part 1A is probably going to take you 5-10 minutes of reading, maybe. Part 2 is where it starts getting interesting. Part 1, you're going to learn about clock glitching. You're going to learn the basics of what a glitch is. Part 2, you're actually going to do it. But you're not going to do a clock glitch, you're going to do a voltage glitch. Be really careful. For part 2, I'm talking about doing fault 2_1, not the 1_2 or 3. I'm not talking about doing parts 2 and 3 of the first experiment. You're going to do fault 2_1, introduction to voltage glitching. And then what I want you to do, and maybe you'll appreciate now why the way I've done some of my labs, or maybe not, maybe you like this style better, everybody's different. I want you to attempt to use the instructions that you're given within the notebook to solve. There's one coding question, I believe, in 2_1. There's only one thing for you to fill in. I want to see if you can do it. Now, don't fret. The folder also has a solution specific to a chipless for Nano for your reference. So if you, I mean, again, not about like torturing you for no reason, but just recognize that instructions differ. I mean, he has a lot of details in some places, and then in other places kind of expects you to make some leaps. So try it out, try to solve it. If you struggle, there is a solution handy. Imagine that as there's another student somewhere in the lab that you can be like, hey, I know you struggled on this for a lot longer than I have. Can you give me some hints? So do that. And what I want you to do in the last cell of that notebook is to basically include a really brief paragraph or two about what a glitch is. What is glitching? What is the experiment that's running in the notebook doing? What do you think it's doing? And then this is a question that's maybe tailored for all of our computer scientists here. And so for those of you that aren't in computer science, reach out and ask, or you can do some searches, or just ask about what is a search algorithm? How might you design a better search algorithm? Which you'll understand a little bit more once you see the actual project. So when you're done, you're going to upload the notebook and/or PDF. You want to do both, I'm fine with that. You're going to upload it at the very least these notebooks back to WildCourses. And I think WildCourses only allows one file, so you'll probably have to zip them. I think that's still a thing in WildCourses. If it's not, you upload them individually. If it only allows you to upload one thing at a time, you'll have to compress /zip and upload. That seem fair? All right, so with that, I'm going to be here and I will take questions while you're going through this on Lab 5 or this Lab 6. Right? So I'm gonna basically for once turn it over to you. Right? I've guided a lot of these labs, but here in a week or two, you're gonna take over in groups doing your own thing. So this is kind of my baby step towards that, right? The transition to all of you, but I'll still be here. So, all right, I've got questions, comments, concerns, issues with the instructions so far. So I can tune them up. Let me at least go to where I'm talking about so you can all see it. So here's Jupiter. Go into Jupiter courses, and we're in Fault 101. The first one I want you to do is at the very top of the list. You can see and read by the titles that you could do some pretty cool things with clock glitching, but don't worry, don't fear. Next week we'll get to do those fun things using voltage glitching as well. So the two notebooks that you're going to be looking at are Fault 1_1 and 2_1. And down here are the solutions. So, and again, you will, if you haven't figured it out yet, there is no solution to 1_1 with the chip whisperer Nano. Right? That's the secret sauce. There is no solution. You can struggle. You can try to find one. If you find one, by the way, let me know. There you go. That's pretty non-committal. If you find a solution, I'd be fascinated. But no, so there you go. I'll turn it over to you. If you want to share your screens, I'll enable that. So if you're working through something and you want to share it with us, if you have a question for the group, feel free. And remember, questions about either Lab 5 or 6, I'll be here. I'm going to stop talking now so that you can actually focus.
I have a question on the glitch module. So, I guess it has all the, let's see, where is it? For the width, I thought it was weird that they have like, you can set the width from like -50 to 50. And I know it said there's not really any good reason to use a width less than 0, but I was wondering why the program would allow it to have like a negative width and why you would even want to do that.
Yeah, that's a really good question. So where are you in the actual, is this in the clock glitching one or down or in the actual?
Yeah, like 1.4.
Yeah, the last segment there.
Yeah.
Yeah, so under width here.
Mhm.
Yeah, so it probably comes down to how they're, I mean, if based off of the offset, when you look at the fact that the range can also be a negative to 50, I mean, -50 to 50, my assumption is that their implementation actually deals with a central point. So imagine that you have I mean, you could probably implement everything without doing it this way, but they're probably saying, you know, if I have um, basically a target point that I want to send a glitch at, there's an amount of time, depending on your hardware, that it would take for your signal to actually spike and reach like basically the maximum amount. So if it's the -50 could actually just be that, you know, you're making it wider and you're starting the trigger.
Oh.
I mean,
Yeah.
I'm reaching here because, again, this is another instance of, you know, like I mentioned a while ago, the developer of the chip whisperer is clearly a hardware guy. So there are some implementation things that might make sense in electronics, but from a programmatic standpoint, like that, I mean,
Yeah.
why, right? I mean, you could have just had your width from 0 to 100. That makes a lot more sense for a width. But if you look at it from the perspective of central point plus or minus some range, you know, that's something that would happen, right? But I don't even know. I mean, right? I mean, it's either that or like somehow it's flipping. Like it'd be interesting to see the implementation. I really don't know, right? I mean, I mean, if you do a negative range, does it actually invert something? It'd be interesting to see the underlying actual implementation of this API call and what it means in the hardware. Be a good experiment if somebody wants to dig in. I've never actually seen a negative range in any of the things I've done. So
Yeah, I was looking at it. It was like the width can be negative. That just didn't make sense to me at first. So I was wondering about that.
nope, I got nothing there. I'll dig in a little bit. I'll do some reading. Doubt it's doubt it'll clear anything up. It's actually worse than that. The glitch width is a percent of the period of time. So now, what does a negative percentage of time even mean? Okay, I'll keep digging, but I'm reading his documentation on a wiki, his own wiki. I'll post the link. So there's the answer. You look at a clock pulse, there's a rising edge or a falling edge in the middle, depending on which way you define your clock, okay? And that is used as the central point. And so he's considering everything to the right of the rising or falling edge as positive, everything to the left as negative. So instead of using the beginning of a clock pulse as a reference point, he's using the center of a clock pulse as the reference point. Peter has the same look that I would have had I not already.
It's very interesting.
Yeah, so there you go. So he's using a reference point that is central to basically to the signal and saying positive values are one way. Basically but yeah, so basically, yeah, anything from to the right of the central point of the, I mean, like I said, either rising or falling edge, it's positive, everything to the left is negative. And there was a mention in one of his things, actually, I might have put it in there. Using a width of 0 is bad. So the documentation actually should say there's no reason to use width equal to 0. Use positive clock glitching. It's a good thing that Chip Whisper Nano doesn't do it. Any other questions or anything that anybody else has seen?
So if you set the width to 0, is that bad because it doesn't actually glitch?
Yeah, you basically cause a, I mean, in theory, if you were super accurate, you would basically cause a spike or some change at the, well, if you do 0%. So the problem is the 0 is actually it's a percentage of the width. They say it's not reliable at that point, right, based off the quote, but I think that if you do 0, it'd be infinitesimally small, and it would probably try to do something right at the center point. Or if it's a divide by 0, again, who knows what the implementation actually looks like. Yeah, 0% would probably not do anything in terms of how long it's going to glitch for. And so. So you can think of a glitch as basically for a region in time interrupting the actual signal. And so if you interrupt for no time at all, I mean, who knows what the implementation will do, right? If you do 0, it might still try to do something. Or like I said, it might try to do it all the time. Yeah. So a 0 wouldn't make sense, but the statement in his, so that I'm highlighting right here doesn't make any sense. There's no reason to use width less than 0. Clearly there is, according to his other documentation. There's no reason to use widths equal to 0, is what this should say. That makes sense. I mean, right, there's no reason to set a 0 width glitch. But you might want to glitch before after the any distance. So really the glitches are going to occur. Use a positive number on the right-hand side of a clock pulse. Use a negative number on the left-hand side. And you wouldn't want to glitch right at the center point because that's already a transition point for the clocking structure. So the only thing you're likely to do glitching at that exact moment in time is extend the signal. I mean, and that's not really the point of a glitch. You're not trying to make the signal higher. You're trying to change the signal. So change where the pulse occurs is all that you would be doing in a glitch. For those of you in 4010, have you that aren't doing those 1.4? Has anybody moved on to default? Even if it's just to check it out. For those of you, I mean, even if you are considering continuing on with Fault 101 while we're on the call, if you want to check out 2.1 or 2_1, so I will give you the hint. I mean, it's not even listed in here. That's how awesome the instructions are. You are going to need to change the scope type and platform type to match our chipless burn nanos. Okay, it's not even listed in here, but you're going to have to do at the very least. First, a lot of commission, so it's not even on. I can get this to work real quick. I have to connect my other machine also. If you have moved on to this section, you actually read what the whole point is. Not that I need extra affirmation or anything, but based off of what you're seeing so far, do you like my style of labs better? I like these. Just curious. Yeah. So Connor, which one are you in right now?
So I'm in fault 2.1, and then I think, let me see. So under 1.1.3, and then it's, yeah, it's the 5th cell. Like if platform is equal to CW light X mega, that one. When I run that cell, that's where it says like the CW Nano object has no attribute clock.
So
I'm getting a kind of similar error in 1.5 that I just posted in the chat. It says no attribute clock underscore source or CLK underscore SRC.
all right, so now here's the question. If you go over to solution 2_1 and you attempt to run the first 5 cells, 5, 6 cells. Do they even look the same?
CW light arm. That's not what we're using.
So if you look, there is a significant difference. So in the instructions, they have basically the firmware path where you actually are going to program the target, right? And then they have this if check, if else for clock gen, right? If you go here, you're going to notice, do the programming. And there's nothing. So this is the segment here, apparently, for the chipless per nano that was clearly not explained here at all. So my best guess, when I ran through this yesterday, it worked just fine. So you can essentially, again, notice that the instructions in his documentation is wonderful for you. This is usually what I take care of when I create our labs. You don't need most of this. And you shouldn't need platform check because we actually know what platform we're doing. And what was the other thing? Yeah, scope IO. Okay. Let me just see the difference here. Make sure it actually works. Yeah, so you don't have a, so this is actually a leftover from last time from not having a clock generation network. So on the chipless per nano, there is no clock gen. You don't have a clock generator because you only have one target and it is always feeding the right clock, which is why we can't do the clock glitches. So what we actually do instead of messing with the clock, everything we're dealing with is just the scope clock output. So that is the biggest difference. So the only code, so let me go back. So this was the code in that cell, all right? Since we know we're dealing with the chipless per nano, get rid of everything here. It's not going to be good enough. That'll be the same. Yeah. So get rid of everything. You can get rid of platform and get rid of clock generation. So you're left with a flush reboot definition. That's one thing. The only other thing you need is, and I mean, this is just the useful thing, scope.io.clockout equals 7.5 e to the 6. That's a capital E. Don't you know this, Peter, you might ask? Connor, you might ask? Trial and error, reading on a forum, looking at the solution at this point for the clock output. Yeah, so this is why we've avoided the author's labs, the author of the chip whisperers labs thus far, because, well, you spend most of your time trying to figure out this. So it should continue to work after that. Let's see where the next place you might see an issue. Couple cells down, the platform type doesn't have chip whisperer nano, so you're probably again going to have to do that. Let's see. Yeah, so you're not going to run. Probably not going to run this last cell here. This one will probably also break. So. And again, remember, if this goes off the rails, if like you cannot get the code this lab author has provided for all chip whisperer users, if you cannot get this to work, don't feel bad. Like literally my weeks are usually converting the labs into something meaningful for a class, right? So this is one of the ones that shouldn't have required more than 2 or 3 changes. If, again, saying it pretty broadly, if you cannot get the lab to work natively, don't feel bad about going to the solution, all right, at all, right? I expect that. I really do. So please, no one be concerned. I promise. Addison also points out it gets wonky again at the clock gen cell. Addison, which notebook are you in right now, and which cell are you looking at? All right, you're all going to force me to boot up what I got done yesterday here. All right, let's see if I can do this. All right, I'm going to join in from this other machine that isn't broken. I'm going to find the Zoom link for this class. All right. So, here is the code that I have for Chip Whisperer Nano, the glitch, introduction to voltage glitching. So this is the working solution. So did somebody say that there was something that wasn't working in this particular area? So this is the cell that was causing the huge amount of problems first, right? The scope dot, I mean, this is the one that had the if checks on in the, let's go back, maybe. So on the original one, there was this if check that didn't work. So that's the first cell that broke for everybody, right? And the solution is essentially to just keep the definition of the reboot flush, to drop all the if checks, just keep that definition, and to set a clock IO. Let's pull it up. Basically do a scope.io clock out. Does that cell work for everybody when they run it? And then if you actually print out the scope parameters, you can see them. Does the next cell run? At what point does it break? Or is it in the other lab that it's breaking? So is it in?
It's the cell that's only in 2.1 and doesn't seem to have an equivalent in 2.1.
Okay.
At the bottom of your screen, scope.glitch. And it has the if, else if.
Yeah. So this one right here. Yeah. So this cell is not, again, the author of the lab has not bothered to mention that none of those matter for the Chip Whisperer Nano, because again, we cannot glitch the clock. So that entire cell is not useful in the Chip Whisperer Nano. Don't you like really clear instructions?
Yeah. Cool.
No, so it's not you, but this is literally, so yeah, so there was a reason why. I mean, I know some of you were wondering, why aren't we just using all the prepackaged labs that the author has, right? It seems like we're doing a lot of the same things. Clearly, there's a slight difference in that I actually tailor the lab. So, but hopefully after you get through that, you're actually going to probably, honestly, let me just save you some work. You're going to struggle right again with all of the loop as well. I mean, he claims, let me pull it up. I don't even think he has it in here. Yeah, basically claims, here you go. Here's the loop, and you should, based off of everything you've seen, you should be able to complete this for loop. And well, not just this for loop, but essentially it's the for loop. The author of Chip Whisperer believes that based off of all the wonderful instructions that have been given the past cells, that you should be able to complete the code here. So with honest opinions here, how would you feel about actually doing that? Well, I mean, honestly, I mean, do you really, I mean, and again, I'm not judging you here because I actually felt the same way. Based off of what you've seen, how confident with what reactions we have available to us? On a clap, thumbs up, crying, joyful, shock, heart, celebration. I mean, how would you actually feel about trying to solve this based off of the information you have? Yeah. Yeah. So luckily for us, we Parker, you got a joyful no. Love it. Yeah, totally agree. So, and this is where I got, let's say, about 3 weeks before the class started. Okay, which is why I decided to do all of this. I really hoped the glitch one wasn't going to be so bad. So, anyways, go over to the solution. Just go to the solution one. I think I've worked my way around it. Just go to the solution one. You can take a look at what he's done. I mean, you can try to look at what he's done, but and do your best to understand based off of the picture that will generate what is actually occurring. So you should actually ultimately end up with something that looks like this: successes and failures. The things to ask yourself are, what are the axes? One of them should be relatively simple, but what is, for example, what is the y-axis here? What is this representing? And it will be generated based off of the code that's down there. There are some hints in his text in terms of what is going on. We aren't focused on glitch attacks this semester, right? They're a whole other ballgame, and glitches are imprecise. So for the past several weeks, we've been talking about actually using, I mean, we've been doing statistical approaches to extracting keys. And now we are essentially going the opposite direction and saying, all right, we're going to just start throwing in glitches, and we now have a non-deterministic approach to extracting information or to causing problems within a system. It is an imprecise world, and it actually can get worse. So right now we're glitching one signal in one dimension. So we're glitching a power line, or we're glitching a clock signal or an input. I mean, we're basically glitching very specific elements. So in this case, just voltage, just one property. There's also EM glitching, where you can basically send electromagnetic pulse into a device. It's kind of like the shotgun approach. You don't even know what you're hitting at that point. So glitching is a kind of an art, and it's not likely something that you're going to actually experience. But it's good to know that some attacks are as simple as modulating the power that goes into a device. But that's really the end objective here, is for you to see that that's possible. And next week, we'll see some things that are a little bit tightened up. Instead of just arbitrary glitching to cause a fault, we'll use glitches to bypass a password check. Right. So based off of our very fun experiences this week in dealing with the author's code, there'll be another handcrafted by Mike. Oh, yeah. All right. So that's what I got. And I know it's not perfect, but know that the answer is there. Focus on trying to understand what is the objective of this, basically this experiment within the glitching lab here. right? Has anybody been able to
Hey,
get?
Dr. Mike.
Yes, please.
Yeah, I have a question here. When we define the groups equal to success, research, and normal, what this means?
So in the group definition, so you
Yeah.
are.
In cell 8. Yeah, cell 8, the second line. Next one. Yeah.
Yep.
Second line.
Yep. So there are potential outcomes for a glitch. So you can either consider a glitch as has caused the easiest one is the glitch has caused the entire device to reset. That's the easiest one to consider. So when you send a power glitch, the device might actually recognize that something very bad has happened, and it will reset itself. Or it'll get into a hung state. It'll get into an unstable state and reset.
Okay.
You might do a glitch and absolutely nothing will happen, right? Like the system just moves along as expected. You didn't cause a problem. Great. The other one, and in terms of from an attack standpoint, is that a glitch caused a fault that didn't cause the system to crash, and therefore it was successful at causing influence. We call that a success from an experimental standpoint. We would call that an attack or a fault or a bypass of logic. So success in this case is a bad thing for a designer.
Okay.
Success means we successfully created a fault or a glitch that caused undesired behavior within the system. So if we had an if check that checked for a password and we were able to cause a glitch that basically caused something else to occur in the system, but not crash the system, that's successful.
Okay.
So those are the three different groups we have. So instead of a binary set, we now have three sets. We tacked it in quotes. It's a success. We broke the chip in terms of we did something so bad that it reset itself, which means our glitch was probably a little too powerful or noticeable. And then the other one is, well, we caused the glitch and normal operation continued. So I mean, in our world, that's kind of basically reset and normal are a failure from an attacker's perspective, but they're a different kind of failure. Because you can imagine that if you cause a glitch and it causes the system to reset, you could be detected.
Mm-hmm.
But if you cause a glitch and you have a successful attack, you can't be detected. If you cause a glitch and normal operation continues with your system, it can't be detected.
Okay, cool.
Yep. Like I said before, glitching is very imprecise. And remember at the very beginning of class, like not this class, but like the semester, I mentioned something to the effect of we're going to focus on passive attacks. And this is the slight shift. We've been doing passive, but I wanted you to see that we can also do active attacks, right? This is active in the sense that we are influencing the system. We have direct influence to the actual operation of the system. And it can be incredibly powerful, right? Because now we can actually start bypassing logic within a system, but it's imprecise and it comes with risks. And if you're doing this manually without a chip whisper, by the way, you have other really big risks. Like there are some safety mechanisms built into the chip whisper platform and logic that prevent us from completely ruining a chip. But in practice, you glitch incorrectly you could basically brick an entire system. So, which would be noticeable in case anybody had any question about that. You all of a sudden destroy a system, it's people know.
So if all these counts are 0, does that mean something has gone horribly wrong?
Yes. Which counts are all 0 for you?
Everything in that cell we were just talking about, the success, reset, and normal.
Okay. So right. So they should all be 0 the first time you run the cell. So when
Oh,
you
good.
run, yeah. So when you first run it, this is just defining the UI. So you're seeing the stats. You'll notice when you run the next cell, the plotting one, it will show up all blank as well. So when you first start this cell, it should look completely blank. The fun stuff happens when you run the very last cell. What will happen when you run the very next cell is all the data above will update. So these are basically like your monitors. And when you run this cell here, the plot updates. So here's the plot, and you'll see that there's a fig.canvas draw that is basically updating this fig up here. And all of the data, so all of the glitch data, essentially you can see that we're adding basically whether it's successful, if it reset, all of that. So there's a print statement, but all of these things are actually updating these counts. This GC count here, this controller is being updated within that for loop. So the zeros are good the first time you run it. They're really bad when you're running the code down below remains 0. But that's a great question, Jared.
That makes a lot more sense now.
What is the y-axis on that plot?
You know what? What do you mean what's the y-axis? I don't know. You're supposed to tell me that, Peter.
Yeah, I know. It's got something about external offset, but I don't know what that means. Glitch setting, I don't, yeah. I'm kind of missing something here.
So there's a range. It says repeat, right? I see there's an external offset that goes from 1 to 200. But then there's another range that's being used that's called repeat.
Oh, that's
So,
all right.
so the question is, we look at
That's weird. And
put it, and I mean I'm hypothesizing. Could be wrong. Would it be a number of times that I repeat an experiment? And I want to see how many times it's successful or not successful at a certain value. I don't know. So one of the questions I would ask, and it might be hard to see, if you were to sum, that's beautiful. How do I do this without giving it away? So what you can do, what you might want to try to do, is you could print out what is being used. You could print out these variables. You can print out what is stored at glitch setting. That might give you some idea of what might actually be happening. You can also maybe read the output that's being presented at the bottom. Or for a lot of fun, there's an example. Where was the example? There was an example in the previous lab. I think it was in 1. In number 1. By the way, if you want to see what should have happened in 1_1, you can look at the solution set there to see what should have happened. But there is a clearly a help function. You can type in things from the chip whisper for scope.glitch here. You could maybe do the same thing for to find out what this repeat actually does.
Yeah, I found the API on their website, so.
You want to post that for everybody? You want to help them out or have them tortured to find it also? I mean, everyone say thank you to Peter.
Yoink! Is there a link straight for that? I don't know. No.
So what did you find? By the way, how I found it, if I can't bother myself to find things on the internet, it's hard. I just type in help scope.glitch.
Yeah, number of glitch pulses to generate per trigger. So we're.
Wait, which one were you curious about?
Oh, the repeat?
Repeat. So here, repeat the width of glitch in cycles also. So we're going to repeat. So how many times are we going to do that?
Okay.
I think that's wrong. Let's see. Oh, you actually looked up for the nano. Look at you.
Woo! Let's run to 8,000-ish. Oh, man. What is going on?
So to be clear, you're asking about this right here. Is that correct, Peter? The scope.glitch.repeat equals glitch setting 0.
Yeah. Well,
So-
yeah, I was trying to understand what the plot was doing initially, or what I was seeing on the plot.
So first off, what is
I mean, I guess you're.
what
further
is
along. There's
what is
the-
glitch setting itself? What is this set to? It's the value of 8. So that's a random number. It's just a number. So the glitch repeat is going to equal 8 all the time. So now, what is scope.glitch.repeat, and how does that influence the plot, right? So you're saying that gets used.
Yeah. Yep.
So and you found online Wait, it's not that simple. So if you look at the code itself, what is being output, you'll notice this glitch setting. What I did was very bad, but I printed out that it equals 8. This glitch setting is a variable. It changes. A glitch setting for gc.glitch values. So we set up an experiment here. Where was it? We set up an experiment in, where did it go? Right here. So we set up the experiment that basically says that we want to have repeat range from 1 to 7. And we want to set the offset from 1 to 200. And we're also going to initialize the repeat to 0. It's probably unnecessary, but anyway, so we're going to do experimental setup here. And then we have this for loop that actually iterates for gc.glitch values. So this would be actually something interesting to actually look at. What this looks like. My guess is going to be a set of arrays, but good, can't see it. Let's see. But ultimately, nope, can't do that. All right, I'm gonna have to find a way to get into there. Oh. But ultimately, what's happening is we're iterating over each potential value for both repeat and offset, right? And we're outputting only in certain instances if we're successful. We're not plotting everything, right? So notice we're not plotting when things are normal. So the plot points that we're seeing are only if it's valid or we have a successful attack. So in theory, if you wanted to plot everything, there should be something at every single point here. It's executing the entire, this entire space. What we're seeing is the width, essentially. It's a change in width. So 7 is the highest width, 1 is the lowest width, based off of that variable repeat. At the lowest levels of repeat, at 1, the width is small. We're seeing the success and failures along that line. And then moving up from there, twice the width. And when we have a super wide width, notice that we get a lot of X's, which are basically resets, and a couple successes. Right? So this axis, the 1 through 7, is actually 7 experiments at 7 different widths. If you really want to see it, you can, for your own fun, you can don't print everything because that's going to be a lot, but you can print an extra 2. This isn't going to work on mine because it's not connected, but you can plot an additional one, and instead of a plus green, you could do, what don't we have? You could do a dot blue, I don't know, or like a line in blue. You could do something in blue, right? Maybe an asterisk. I think asterisks will do something fun. So you could plot all the other points in this matrix as well. If you really wanted to see that the whole matrix is going to be filled for every experiment. Basically, you're sweeping through the entire space, and you have one of three options that's going to come out. It's either going to be the successful green plus, which is where we were able to attack. It'll be the red X if you accidentally reset the device. And everything else, normal operation, normally wouldn't show up at all. But if you want to do a blue dot for normal operation, you could plot that too. So then you get a picture of where's the normal operation of the device, even under glitching. Where does it get reset? Resets are bad. And greens are successful attacks. Giving you so much. Anybody who watches 2 minutes beyond the end of class is going to have all the secrets.
So does that mean with like repeat 3 and 4, that's like total normal operation?
Yep.
All right.
So you might want to, I mean, so for hardware designers, you might want to think why that might be, but essentially, I mean, okay, I know we're not all hardware designers. We're not hardware designers here in general. 3 to 4 might be the sweet spot of you've basically just doubled the clock rate, and it actually, you happen to hit a sweet spot where there is no influence. It is my best guess, by the way. So you cause it a pulse at a point that actually has no bearing on the circuitry at all. So, yeah. What's super fascinating though, right, is you've got some ultra low ones that do have impact. Those are just the right point. But again, it's this is where the kind of an art. There's understanding the why would take a lot of effort here, right? You'd actually have to go and start peeling away and looking at the actual hardware logic. And do a whole lot of simulations to figure out the behavior of why something was or wasn't working. The chip designer would be fascinated by this. But there does appear to be a sweet spot regardless, right? At about 150, what is it, 52.
Yeah, mine's different. I mean, I've got all those green pluses, but I also have a lot of resets mixed in. So there's not like a clear area where you're going to get glitching and not resets. They're so close to each other that you'd be threading the needle.
Yeah, it'd be interesting to rerun it, honestly, Peter. I mean, like there's not a, yeah, I mean, oh, the one thing to check. Do you check, I mean, this shouldn't be a huge difference. Check your I mean, that's actually, sorry, no. Yeah, just try, I mean, I would honestly say try rerunning it. And remember that we are dealing with sensitive hardware. We've noticed in the past couple of weeks, and I know we're well over, by the way. In the past couple of weeks, we have noticed some differences in our hardware, right? In terms of some people can't do some of the experiments in the same number of traces. These are pretty sensitive pieces of equipment. The author, the developer, claims that you should treat these with anti-static procedures all the time, and I'm like, mine randomly hangs out in my bag loosely, so I have definitely not treated mine nicely. So yeah, definitely there's going to be some variation here, and glitching in itself is a very finicky thing, right? It's not nearly as but yeah, so hopefully you all now maybe appreciate my lab slightly more. I don't know. Or not. But if you have questions, let me know. And remember, the answer to the code is there actually for both labs. Try to take some time to unwind and figure out what's going on. It might take some, as you just saw Peter and I do, looking back at the documentation to try to get some idea and some sense of what's happening. And hopefully that gives you a little bit to go off of. And remember, the point of this class is not the glitching attacks, but they're cool enough that I thought you'd want to see them. All right. All I've got for you. Enjoy your weekend. If you end up looking at the fixed assignment, you're like, yeah, it'd be nice to have more than 2 weeks. Let me know. I mean, I'm flexible there. It shouldn't be too bad. Yeah. All right. Have a good weekend, everybody.
Thank you.
Okay.
Thanks.
Absolutely.